Yeah. So I think we completed till over here. Like, what is the magnetic field of solenoid? Till here we completed, isn't it? Now, when we were defining magnetic field of solenoid, like we told, like, sir, there is a some magnetic field which will exist in the solenoid. But question arises that this magnetic field, which is B is equal to mu naught Ni, which is also equal to mu naught capital Ni by L, is going to exist where and where? Okay. So let us suppose that if I have a solenoid, can you see the image? And some kind of current is entering. Then here also, first thing is remember that you need to apply right hand thumb rule to find the direction of magnetic field. Okay. Here also you'll apply the same right hand thumb rule. Are you able to get me or not? So look over here. Let's suppose if I rotate it, if I put the thumb along the direction of, if I curl along the direction of current, then we'll find that the magnetic field direction inside it is going like this way. Got it or not? Got it? So if you put the thumb like this way and you curl it, then you will feel that the currents are going like this way. Are you able to get magnetic field is going like west side? Is that clear? Now, one of the most important thing to remember that although some magnetic field lines exist outside of the solenoid, but the gaps where the magnetic field line does not exist, we consider them there at that point, the magnetic field due to the solenoid to be equal to how much? Zero. Are you able to get me or not? So you remember that near perpendicular distance of solenoid, the magnetic field is zero. Are you able to get me? Whenever I'll consider a near perpendicular distance of any kind of a solenoid, the magnetic field is always going to be equal to how much? Zero over there. Are you able to get me or not? Is it clear? Yeah. Write it fast. Okay. Now, second thing to grasp over here is like, okay, this was the case of solenoid. That's fine. That's good. Okay. But let's suppose another kind of example is, let's suppose if I have a hollow cylinder. Okay. If I have some kind of a hollow cylinder, or I don't know, then for that hollow cylinder also, I mean, remember, let's suppose if this is my hollow cylinder, okay, can you see? Now, if there is a axis axis over here, let's suppose this is my axis, then here also, basically, if I consider that if current through the hollow cylinder passes through the surface, or you can say if the current in the hollow cylinder is along the curved surface, where it is, yeah, along the curved surface, right or not? Let me draw it. I think there is some curved arrow. There is no curved arrow. I think there is no curved arrow. Okay. So let me draw. So let's suppose the current is flowing like this way along this curved surface. Right or not? Got it. And let's suppose this current is I. Then this cylinder, then this cylinder works like solenoid. So no need to prove it. Okay. Yeah. Whole cylinder works like solenoid. Is that clear? Yeah. So here you can see that the number of loops is always 1, and therefore, let's suppose if the length of the cylinder is L, got it? So magnetic field over here is given as mu naught I by R. Are you able to get me or not? This is the formula. Is that clear? So you should learn it. No need to prove it. Are you able to get me? Is that clear? Next kind of a binding material is our toroids. Okay. Yeah. So toroids are, remember that when I consider an example of a toroid or something like that, then here the particular binding is like a circular turn on a particular kind of a thick material. Are you able to get me or not? Okay, now if I consider, let's suppose here R is given to you of the center, but what if the inner center is known and outer center is given? Are you able to get me or not? Inner radius is given and outer radius is given. So here if R is mentioned for the toroid, no problem. But what if inner radius and outer radius are mentioned? So remember that if outer radius and inner radius be R1 and R2, then radius of toroid, which is given as capital what? So that radi- so it is R1 plus R2 divided by 2. Are you able to get me or not? There is no derivation. Just learn it. Word up. Like earlier we defined for every case, like how to define for solenoid and all or not. So magnetic field was we were defining B is equal to B dot dl is equal to mu naught Ni. Are you able to get me or not? Mu naught I. So here dl is just the length element L. Are you able to get me or not? So here if I look over here, if I apply Ampere's circuit law, then integral B dot dl is equal to mu naught I enclosed. Are you able to get me or not? But there are n number of turns, so mu naught Ni enclosed. Are you able to get me or not? And here dl, if I took, yeah, 2 pi r, so mu naught I, and so therefore B is equal to mu naught I n by 2 pi r. Are you able to get me or not? Is this clear or not? Yeah. Okay. So I define toroids. Now, as you know, if number of units, if number, you can say that if number of, if I define n as number of turns per unit length, so here n will be exactly equal to n by 2 pi r, and ultimately B will be written as mu naught small n I. Are you able to get me or not? That's the formula of solenoid and toroid. Is that clear? Write it first. Per unit length. Yeah. Okay. Now look over here. So right now we are defining for different cases, different types of materials. Got it or not? The third kind of material which I want to discuss is not given in any books, but is very necessary to understand, and that is magnetic field of infinite long set. Srishti, tomorrow you have the class at 11:30 or 12. Okay, a.m. morning. 11 or 11:30. 11, no, not 11. 11:30 or 12. You do not have class, no? So if because evening I'll be totally busy. Word or not? Ah, but yeah, and we'll have to plan perfectly that how to complete our those sessions of rotation and all. Okay, I'm planning, but it's not getting executed. Okay, I'll see anyhow. Let me check. Let me plan it perfectly. Now see, this is an infinite long set. I'm just considering the one of the side view of it. Which view I'm considering? Side view. Are you able to get me or not? So basically, this is the width part which I'm considering. Okay, and current is going like this way. This is some kind of a seat like this way. Got it? And current is flowing like this way. Got it or not? And I'm looking over here. This thickness. Got it or not? Yeah. So I'm looking at the thickness. Inside that, the current is flowing. And let's suppose the width of the material is given to you. Are you able to get me or not? Then you know that for these kind, again, you know that for any kind of a current, let's suppose this is my C and current is going like this way. Go ahead or not. So magnetic field will exist in the perpendicular direction to the seat or not, like this way. Are you able to get me? Applying right hand thumb rule, isn't it? So if I select any point perpendicular to the width, then I'll find out that some magnetic field is existing over here, independent of distance from the seat. Are you able to get me or not? Inde- Independent from distance from seat. Are you able to get me? Yeah. So here some magnetic field will exist in this direction, while here it will be existing in this direction. And let's suppose if I define my lambda, a new kind of a charge density. Basically, it is not charge density; it is current. Yeah, current per unit weight. Right or not? Are you able to get me? Then the magnetic field over here is given as B is equal to mu naught lambda by 2. The formula is B is equal to mu naught lambda by 2 and it is always uniform. Are you able to get me? This is a very big derivation. It depends on uh, boundary conditions, void or not. So I'm giving you this task to search for its derivation. Otherwise, I'll discuss one day definitely. Are you able to get me or not? But you should remember that yes, for a current carrying along the seat also, magnetic field exists and it is exactly equal to B is equal to mu naught lambda by 2. Where lambda is the current per unit. Yeah, are you able to get me? Is this clear? Okay. So now, so till this time, we did a very large thing. We completed solenoid, we completed different kind of geometrical figures, we completed Ampere circuit law, Bart-Savitz's law is even completed. Everything is completed. But we didn't talk about the independent charges, isn't it? So now our single charges. Now the whole thing is, earlier it was magnetic field due to current. Now we are going to understand the magnetic field due to the charges. Are you able to get me or not? So give the heading magnetic field due to moving charges. We can give, it is also called as equivalent current concept. Okay. So earlier in the first class, we talked something related to movement of charges. Got it or not? Got it? Like how the movement of charges used to generate the magnetic field. We talked quite about that, and it was given as B is equal to mu naught by 4 pi QV sin theta by R square, isn't it? We are going to pick up all of those, and we are going to make us understand how to utilize all these things. Got it or not? So first case, now earlier the charges were moving randomly here and there, but now we'll start considering a special kind of movement of charges. The first one is called as charge, yeah, charge moving on a circle. Means, see, earlier it was randomly moving, but right now we'll consider one or two examples where it moves in a particular way. Got it or not? Yeah. So like right now we considered if a charge is moving in a circular way. Got it or not? Is that clear? So look over here. If the charge is moving in a circular way, what will happen? Let's suppose if the radius of the wire is r, alright, and there is a charge over here, charge q, which has some velocity in forward direction, tangential to the circular loop. Are you able to get me or not? If it is having some means velocity, definitely it means it is rotating with some angular velocity omega, isn't it? Are you able to get me or not? So basically, question arises that what is the formula of equivalent current? First, you should define your current, isn't it? Yeah. First thing, if a charge rotates on a circular loop, what is the current defined over here? Tell me. Per unit area or charge by time? If radius is given, so I is equal to what is time? 2 pi r by v. So qv by 2 pi r. But what is v by r? V is equal to r omega or not? So this implies q omega by 2 pi. So magnetic field at the center due to current in a circular loop is given as what? Mu naught I by 2 r. Isn't it or not? Put it mu naught q omega 2 goes up 4 pi r. That's my magnetic field at the center when a charge rotates in a circular way. Got it or not? Is this clear? We can also calculate this with that formula where we wrote D is equal to, what was that formula? Mu naught by 4 pi Q V cross R by R cube. Isn't it or not? So here it is what? Mu naught by 4 pi Q V, and V is perpendicular to R. So I can write sine 90, isn't it? By R square directly. But what is V by R? Omega. So it is mu naught Q omega by 4 pi R. From here also you can find it. Are you able to get me or not? Is that clear? Now look over here. So first, second, third. Let's talk about electric field at the center. What is the electric field at the center? Tell me. Is the center O is at same distance R from the charge? So it will be simply KQ by R square. So 1 by 4 pi epsilon naught Q by. So this means that magnetic field depends on movement of charge, isn't it? But why this is independent? Are you able to get me or not? Independent of movement of charge. Are you able to get me? So let's suppose if I want to take, so you can write like this way. Basically, in anything, electric field is independent of motion of charges, right or not? While looking at the magnetic field is dependent on motion of charges. Right or not? Write it fast. So from here, I can calculate the last important conclusion, that is the ratio of, yeah, electric field and magnetic field for moving charge. You see that when you calculate E by B, that is basically equal to how much? If you do it, E by B. So uh, this Q omega by pi 4 pi R will cancel each other, isn't it? So what I'll be left, if you look over it, let us write E is 1 by 4 pi epsilon naught Q by R square, while B is mu naught Q omega by 4 pi R. 4 pi cancel, R cancel, Q cancel. So I got what? 1 omega, wait, it will be 1 by epsilon naught mu naught omega into R. What is omega into R? Velocity or not? Yes. So this is 1 by um, uh, epsilon naught mu naught by velocity v. Are you able to get me or not? But then we define this whole thing as c square by v. So E by B, from here, I'll tell you, we define from here a quantity called as speed of light, which is called as c, and that is nothing but 1 by root over mu naught epsilon naught. Are you able to get me or not? And therefore, E by B always provides you for a moving charge speed of light. Is that clear or not? V is the velocity of the charge, but the velocity of charge will generate a speed of light. Are you able to get me or not? So moving charge generates what? Speed of light. Are you able to get me? Clear or not? So this thing which I did right now, it's something very, 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 very awesome. It's not written in any of the books. If you read 1,000 times also, you will not get it. It's written in David Morey, something like that kind of books. Word or not? This page itself is something which is not written in a perfect way in any of the books. But this is the crux of all those books which are there in like those books which are written by scientists in the world. Word or not? That the movement of a charge generates my speed of light. Are you able to get me or not? Is that clear? When I move ahead, okay. Let us discuss the second case. So first case, charge was moving. Second case, there is a charged ring rotating about its own axis. Hold on, there is a ring this time. Hold on. And this ring is rotating about its own axis. Are you able to get me or not? So let's suppose if the radius of the ring is r, I'm considering the radius directly. I'm not considering inner or outer, something like that. Got it? And it is rotating about its own axis with angular velocity omega. Now consider that the ring has some charge on its surface. It was a charged ring. So then tell me the magnetic field at the center. Tell me fast. Yes. U not I by 2r. Think once again. Charged ring rotating about its own axis. Okay, let us first define the current. Because to find the magnetic field, I need the current. I is equal to charge by time. Once again, it is same. Charge time is simple. 2 pi r by v. Although it is rotating, so it will rotate with omega. R by v is omega. So q omega by 2 pi. So magnetic field is still same. Mu naught. Yeah, what was the formula? Mu naught I by 2r. Mu naught q omega by 4 pi r. While the electric field at the center is O. is how much? Zero. Because for the ring, all the electric field cancels each other, isn't it? Third case, charged disk. I think charged disk will take a lot of integration. Okay, so let us do it separately. The third example of it, just consider a charged disk rotating about its own axis. So let's say there is a disk, a charged disk I have, void or not, and it's rotating about its own axis, void or not. So look over here. Let's suppose this is its center and it's rotating with angular velocity omega with respect to its center. Radius r is given to you. Then find and consider that the total charge present on the disk is plus sigma and total charge present is plus q and surface charge density is sigma. Then find the magnetic field at the center of. Do it. Tell me what will be the answer. What? Okay, first of all, there's a mistake. You see one thing over here before consideration. Let me make you understand. What is the formula of velocity in terms of omega and r? V is equal to r omega. What's the meaning of that? What is the meaning of that? You didn't told me. V is equal to r omega, isn't it? Means as radius changes, if the center is rotating with omega, so as my radius will change, does the velocity should change? Velocity should also change. That means If I consider 2 to 3 different points, point P1, point P2, point P3, all these points have same velocity or different velocity? They have different velocities. Are you able to get me or not? Where V1 is more than V2 and V2 is more than V3. So does the charge over here has the same velocities? Tell me, does the charge over on the whole surface of the disk is having same velocity? The answer is no. The charge is having different velocities. Are you able to get me or not? So how to find simple? First you need to consider as we know that this is a whole disk. Then the first target is to consider a ring element over here. Are you able to get me or not? And then you can do the calculation. So let's suppose this is my bigger disk. Okay. I don't know. So I'll consider a ring element over here. Such that its velocity is constant. Its velocity is not changing. So let's suppose the radius of this ring is r, a small r, but the width of this ring is dr. Word or not? So I need to first find charge in this ring or not. Let's suppose call as charge as dq. So as sigma is same, for the ring also sigma must be same. So dq by dA must be equal to total charge by total area, isn't it? So dq by dA I have told total length is 2 pi r, width is dr. Area is length into breadth or not? So 2 pi r into dr is equal to charge by pi capital R square. Pi cancel. So dq is equal to how much? 2 r q dr divided by r square. Are you able to get me? Clear? And this dq is rotating. So current generated due to this will be very small. So current due to dq is what? A small current which is di, which is dq by time period t. dq is twice rq dr, or let me write it like this way: 2q r dr divided by r square. Time period is what? 2 pi by omega. Are you able to get me or not? So what I'll get? Twice q omega r dr divided by 2 pi r square. Are you able to get me? So for this, I'll get a small magnetic field or not? I'll get dV, which is mu naught di by 2r. So what I got? 2 cancel. Mu naught by pi r cube q omega r dr. Are you able to get me or not? Now, to find the net magnetic field, I need to do just the integration. So therefore, B net is integral dV. So that varies from, so these things are constant. So mu naught q omega by pi r cube outside 0 to capital R r dr. So what I got? Mu naught q omega by pi r cube r square by how much? 2. Is that clear? So what I got? B net ultimately mu naught q omega by 2 pi r. So earlier, due to the ring case, it was mu naught q omega by 4 pi r. Now it is 2 pi r or not. So this means that magnetic field at the center of disk is more than magnetic field at the center of ring. Many people think that the magnetic field due to the rotating disk will not exist, but it is more actually. Are you able to get me or not? Because it is a continuous object and magnetic field does not exist on the continuous object. They think like that, but it is not true. Yeah. Are you able to get me? Write it fast. So now, ultimately, one more last term. Let me erase this and write it that magnetic field at the center of this is more than magnetic field at the center of ring. Last point is when I express this magnetic field, it is expressed in two ways. D net of the disk in sigma, it will be written as sigma will be q by pi r square or not. So what I'll get? Make pi r square, I'll get mu naught sigma omega r by 2. Are you able to get me or not? While it is equal to mu naught q omega by 2 pi r. So there are two conclusions over here. First conclusion, when sigma is given constant. Are you able to get me or not? So in that case, the magnetic field is directly proportional to radius r. See that? Is that clear? Second case, when charge is given constant, inversely pro yeah, remember. Clear? Right. Right. Done? Okay. So let us do one example. So this is your case only. A rotating hollow cylinder. So let's suppose if I have a hollow cylinder, got it, and I'm rotating it along its axis, got it or not? It's rotating with angular velocity of omega. Let's suppose if it has having some charge q on the curved surface and the length of the cylinder is L, then find the magnetic field and electric field. Magnetic field and electric field. Basically, in earlier case, here we defined magnetic field, but we didn't define electric field. Electric field to the disk, you know that it is always same. It is given as sigma by 2 epsilon naught, isn't it? On the center, basically. On the axis, it is totally different, isn't it? So here also we define magnetic field and electric field. Good. Yes, but where it is? Is it outside or inside? Is it at the center? Along the curved surface? Right now, I told you hollow cylinder is like a solenoid. So solenoid, right now I discussed outside there is no magnetic field. Yes, so inside magnetic field is what? Mu naught Ni or mu naught I by L, isn't it? Mu naught I is what? This whole charge is rotating like omega, yes. To pi L into omega. Are you able to get me or not? This is clear. Here opposite happens with the electric field. Electric field outside is zero. Sorry, outside exists, which is 2k, yeah, 2k lambda by r. Yeah, while E inside is zero. Yes. So it does not implies where electric field is zero, magnetic field is also zero. Remember that. There was a assertion and reason in NEET 2021 that if electric field is zero, magnetic field is zero. No, that's not sure for a rotating hollow cylinder. Are you able to get me or not? Yeah, yeah. Is this clear? Okay, let us discuss another case. Moving rod or cylinder. Yeah, this time it is. Okay, so let's say this is a rod which carries some charge. Okay, carries the plus charge and the length of the rod is L or the length of the cylinder is L. It's moving with some velocity V like this way. So then find the electric field inside the rod, outside the rod, magnetic field inside the rod, outside the rod, or magnetic field inside the cylinder, outside the cylinder, or something like that. Everything has the same answer. Yeah. Rod or cylinder you can consider like that. The rod is also the same thing. Like it will have a hollow thing inside. Okay. 1 minute, I'll take a break. Okay, try to do it. Hello, can you hear me? Okay, yeah, go ahead. Under what situation? We do not know. We do not know. You have to tell. Okay. Electric field. What is the case when electric field will be similar to magnetic field, isn't it? Okay. Electric field is due to which thing? Rest charges or moving charges? We defined electrostatic field, now. Ah, and magnetic field is due to. So I'm damn sure that they will never be similar. But yes, one can be zero and another can be non-zero, but they will never be equal to each other. Are you able to get me or not? Something. Yes, yes. For all situation, no. Like here, when we have magnetic field inside, I have a some value. At that point, electric field is zero. It might be zero, it might not be zero. It depends on the rod. Okay. So let us see, let us see. Basically, if you look over here, this charge is moving with some velocity over here. So that means that the direction of current is along this side, isn't it? Correct? So question arises that what is this amount of current? So let's suppose, yeah, let me write the, let's suppose some charge passes through, what will be that? Can you tell me what is the amount of current? No, this, why 2 pi r will come suddenly? It's a cylinder or anything, but charge will, is the charge is rotating, moving with the velocity. So let's define. So charge passing through the cross section. So that means that some amount of charge passes through some cross sectional area, isn't it? So charge passing through cross section in dt time is how much charge passes. Basically, it will pass dq amount of charge, isn't it? That will be equal to how much? Total charge is present in total length L, isn't it? But here area of cross section will have width how much? It will be v dt or not? Tell me yes or no. So dq is equal to total charge per unit length into area, which is or length of the particular cross section, which is v dt. Are you able to get me or not? Once again, I'll see you. See. Basically, some amount of charges are crossing, like, isn't it? And this is my area of cross section. So question arises that in a very small time interval, how much charge passes? So those number of charges which are present in this particular length, which is created by VDT, length of that particular cross section is VDT or not. So whatever will be the charge present in this region, that will only pass or not. So this is why the length I'm considering to be VDT. Are you able to get me? And total charge per unit length is Q by L. So amount of charges passing through that length is Q by L into V dt. Are you able to get me or not? So therefore, I is equal to dq by dt. So it is equal to qv by L. Or you can also say as I is equal to q by time period. Q and time period is what? How much charge will pass basically through some reason. Let's suppose that time period to cross this length is v by basically what will be that L by V. So therefore I can write it as qb by L. Are you able to get me or not? So I got my current. I got my what? Current. Now magnetic field at the center, it is equal to how much? So let's suppose if I am considering magnetic field not center, let us consider magnetic field outside the rod. Here it is not a solenoid because current is not rotating, isn't it? So magnetic field outside the rod is existing, that is mu naught I by 2 pi r. Yeah, because here this time current is along the axis of the rod. Are you able to get me or not? So is this clear? So this is B in outside of rod. Are you able to get me? Second point, if I talk about B inside of rod, then it is 0 if the rod is hollow. And yeah, and it is equal to, remember that it is equal to mu naught J R by 2 if it is solid, just like solid cylinder. So everything is same, word or not? Where J is the I by V, I by area A. Are you able to get me? Similarly, we know that the electric field of this rod is also defined. So electric field of a rod or cylinder outside is always same. E outside is simple 2k lambda by r. But E inside for hollow case it is exactly equal to 0. But E inside for solid case it is not 0. It is equal to rho r by 2 epsilon naught, isn't it? For solid. Are you able to get me or not? Is it clear totally? Right, let it pass. 1 minute. If you have doubt, you ask me. Check once. So many things we have done. Please check once. Then I'll. Yeah, because it is not rotating. Rotating means it will work like a solenoid. But if it is not, because if it is rotating, the current is generated like this way, like turning current. But here the current is generated like straight way. Yeah. Can I move ahead? Now give the heading. Last part, that is moving charged seat. Heard or not? So let's suppose if I have a seat. Okay. And Srishti, just after your tests are over, complete the NCRT of each chapter. Got it or not? Seventh test is over. Take 1 day and complete the NCRT of electrostats, then capacitance, and then 1 day current, electricity, and all. Got it or not? So basically, look over here. If this is a charge set, then it has a uniform charge density sigma. Got it or not? You consider it to be having length L. This to be breadth B. Got it or not? And it's moving with some velocity V. Then I ask you find the magnetic field. Yeah, anywhere, define. It's your task. Can I help or can you do it? Try it. Okay, let us see. Let us see. Now, once again, here the charge is of different way, word or not. See how the charge will appear. After some time, this will go over here or not. Yes. So this thing, this area, this length is covered how much? It is simple VDT. So DQ. Earlier the charge was in what length? Charge was in total. Let's suppose due to this sigma, the charge was Q by area, which is B into L. Then I need to consider the small area, that is B into V into dt, because breadth is still same. Are you able to get me or not? So this is Q by L V dt. Right or not? So therefore I is equal to dq by, which is QV by L. Are you able to get me or not? Now, basically, I can determine with this QV by L, or I can also determine with respect to our, you can say, sigma also. Are you able to get me or not? As sigma is given, so this can be also written as dq is equal to sigma dv dt. Are you able to get me or not? So I, which is dq by dt, is given as sigma b into velocity v. Are you able to get me or not? Now, as you know that for any kind of a seed, right now we defined magnetic field is given as mu naught lambda by 2, where lambda is current per unit width. So I need to define lambda. So if I define lambda, lambda is current per unit width, which is B. Sorry, length L, isn't it? No, no, no. Width is not length L. Width is B. Are you able to get me or not? So this is QV by BL. Are you able to get me or not? And here if I define lambda, lambda star, let's suppose it is sigma BV by B. So it is simply sigma B. Are you able to get me or not? Clear? And here if I define magnetic field, it is mu naught lambda by 2, isn't it? So it is mu naught QV by twice PL. Are you able to get me or not? And here it is mu naught lambda by 2. So it is mu naught sigma V by 2. Are you able to get me or not? So this is my magnetic field due to my infinite seat, or some kind of a seat. And electric field, it is given as always sigma by 2. Clear or not? So this was about your all the different kinds of equivalent current concepts which happens for different types of materials. Is that clear? Confirm? Write it. Okay. Now the last part of this, and we call it as Gauss law of magnetism. Got it? So it's also same thing. It says that net magnetic flux got it? Net magnetic flux through any closed surface word or not is always instead of earlier we used to consider, it is this time always zero. It is always how much? Zero. So therefore phi, when I define, which is integral b dot dA, it is always how much? Zero. Because what actually exists? Ampere circuital law exists. That is why b dot dl exists. Are you able to get me or not? Are you able to get me? So due to this, I can define our magnetic field energy density word or not. So simple, magnetic field energy density will be given as, just like earlier it was E square by epsilon naught. Here it is B square by twice mu naught. Are you able to get me? Is that clear? And therefore, simply just magnetic field energy is given as B square by twice mu naught into some volume, or it can be also written as B square by twice mu naught dV. Are you able to get me or not? So where V is, this V is volume. This V is caps V, which is volume. Are you able to get me or not? Got it? This was all about your Gauss law of magnetism and all those kind of things. Is that clear or not? So I'm left out with one question of solenoid, and then we'll start. So today we learned how to find the magnetic field due to charge. But as a charge is placed in magnetic field also, it will experience some force or not. So tomorrow onwards we'll pick up that how the charges will feel the force if they are kept in a magnetic field. So today we learned how to generate the magnetic field. Now tomorrow onwards we'll learn how the charge will feel the force in the magnetic field. Is that clear or not? Okay.